We're going to continue to look at our series and take a look at some of the tests to help us determine whether or not a series converges or diverges. So far we've seen two types of series to where if we could recognize their form, say a telescoping or geometric series, then we could determine whether or not they converge or diverge. But those were two specific types of series. We're going to start taking a look at some more all-purpose tests that work on basically any type of series out there. The first test we're going to look at is called the nth term test. Here's the idea for the nth term test. If I have some summation 1 to infinity of a sub n, now remember this is a1 plus a2 plus a3 plus all the way out forever. I'm just going to say a sub n. Remember that goes out forever. Doesn't it seem reasonable that for this to add up to be a finite number, that these values have to be heading towards 0, or a sub n has to go to 0 as n goes to infinity? So the nth term test says this: for a series to have a chance to converge, the limit as n goes to infinity of a sub n has to be 0. Now here's the big key here, and this is what most students miss. This is just to have a chance to converge. This does not tell you whether or not a series converges or diverges. However, if the lit as n goes to infinity of a sub n is not 0, that does tell us something very specific. Then n equals something to infinity of a sub n diverges. Okay, so here's where you're going to make your mistakes using the nth term test. This is always the test you want to do first because it's really quick and easy. A lot of times you can do it in your head. You're going to say, okay, if the limit of a sub n, if it's not 0, then you can say it diverges. If it is 0, you can't say anything. That just means you got to keep going. So here's the appropriate way to do this test. Let's take a look at it. So I'm going to say use the nth term test, which again, this should be always the first thing you're looking at unless you recognize it's geometric or something like that. Right? So let's say if I say it's the sum, n equals, I don't care, let's say 4 to infinity of n over n plus 1. Well, in our head, we're just going to say, okay, what is the limit as n goes to infinity of n over n plus 1? Now you can go and do L'Hopital's rule and all that other stuff, or you can just use some common sense here and say, as n goes out towards infinity, like ridiculously large numbers, so on the bottom, think about this, we'd have 100 billion, zillion, gazillion, billion, zillion, zillions, plus 1. Right, that plus 1's not going to make any sense, right? So really, as we head out towards infinity, this just starts looking like n over n, which is 1. So since this is not 0, we can say that this diverges. We don't have to do anything else at all. That's it. It diverges. Our work is done. However, if we had this, let's say we had the sum n equals 0 to infinity n over n squared plus 1, well, that's the limit as n goes to infinity of n over n squared plus 1. Again, you can kind of think about this as we go to infinity, that plus 1's really not going to make any difference. So that's n over n squared, which is the same as 1 over n. So what happens to 1 over n as n goes to infinity? Well, that gets smaller and smaller and smaller. This goes towards 0. So what does that tell us? Well, that doesn't tell us anything. That tells us absolutely nothing. This right here could either converge or diverge. It could go either way. So this actually tells us nothing. This just means keep going and use other tests. So this tells you nothing. But as you see, it's generally very quick and easy to do, and it can get you out of some problems very, very fast. So you do always want to try the nth term test first. But there are other tests that will tell us whether or not stuff converges or diverges. So let's go to our next test. It's called the integral test. Now, here's the concept, a real quick concept of an integral test. We already had the idea as an infinite integral, like from 1 to infinity. We're looking for the area under a curve, right? And we know that if this adds up to a finite value, we say it converges. If it adds up to an infinite value, we say it diverges. Same idea as our series. Well, if you think of our a sub n's as specific points on here, kind of like here, 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 you can think about what we originally did in Calc 1 as making these as rectangles. Since each one of these has a width of 1, the area of the rectangle is really just the height of the curve there. So the area of each one of these rectangles is the exact same thing as adding up the values of each one of those points, or doing the original summation. So you can see that the area beneath the curve, in the way that I have it drawn in this case, is actually bigger than the area of the rectangles, which means that the area under the curve converges. That means the area of these rectangles has to converge, or the area of the summation has to occur. Now, if we use the right side, it'd actually be a little bit over, but we can actually fix that by just pulling out the first term. I'm not going to go through all that. I just wanted the basic idea. So to use our integral test, so first off, for our integral test, let's let f sub n equal a sub n, right? Our a sub n, some function of n like we've seen before. If a sub n is equal to some f sub n, and let's say if f sub x, now I got to go to a continuous variable because I'm going to integrate. So that's why I'm switching x. If f of x is positive, excuse me, decreasing, and continuous on the interval. Now what I mean by interval, the interval for our summation, so like from 0 to infinity, then if the integral from wherever, I'm just going to go from a to infinity of f of x dx converges, then the sum n equals a to infinity of a sub n converges. Now, your textbook, at least most textbooks here, put a 1 right here where I have the a. That makes it a little bit easier for them to do the proof of this, but it really doesn't matter what that bottom number is. In fact, it doesn't matter if it's decreasing the entire time. It just has to be decreasing some point from a to infinity and after that. It doesn't have to be decreasing always, just decreasing after a point. All right, but let's go ahead and see how this works. So let's try a couple of these. Let's say I have the sum n equals 1 to infinity 1 over n squared plus 1. All right, and we're told to determine if this converges or diverges. That converge or diverge. Well, one of our tests is our integral test. So here's what we're going to do. We're going to say, let's let f of x equal 1 over x squared plus 1. Now here's kind of the tricky spot. Now remember, we're looking for this on the interval from 1 to infinity. So on the interval from 1 to infinity. Now positive is generally something that you can just state by looking at the function. All right, the top's always positive, something squared plus 1 is always positive, so this is positive. But you do need to state that. You need to say that, okay, this thing's positive. Now decreasing, how do you tell that something's decreasing? The easiest way to do that for most of our examples is going to be taking a look at the derivative. So if I take a look at f, I'm going to go ahead and write f of x over here. I'm going to write this as x squared plus 1. I have it written. X squared plus 1 to the negative 1. F prime of x would be negative x squared plus 1 to the negative 2, or negative 1 over x squared plus 1 squared. Okay, so there's our derivative, or the slope of our tangent line. And we can see the top is always negative, the bottom is always positive. So this is always less than 0. In fact, for any value of x. But this is definitely less than 0 from 1 to infinity. Since that's less than 0, we know that the function has to always be decreasing. So there we go, we've proved that it is decreasing. And then we also have to talk about its continuity. Well, this thing is continuous everywhere, right? We never divide by 0, so it is. Now, it seems pretty small, that little piece, but anytime you do the integral test, you have to justify all three of these. Now, most of the time, just stating it's always positive is enough. You better be careful. If it's not, you get it wrong. To tell if it's decreasing, take a look at the derivative. And continuity, generally, you can tell by looking at it. So what does this mean then? Now, since it fits all three of these, then we should be able to do the integral from, since we're summing from 1 to infinity, we want to integrate from 1 to infinity, 1 over 1 plus x squared dx. Well, this is an improper integral, so we want to do the limit as b goes to infinity, 1 to b, 1 over x squared plus 1 dx. To get our side work out of here. All right, so this is a known integral. We should know how to do this by now. That's our arctangent. So this is going to be the arctangent of x evaluated from 1 to b. So the limit as b goes to infinity, that's the arctangent of b minus the arctangent of 1. Okay, so as b goes to infinity, what is the arctangent of infinity? Now, the easiest way to think about this is picture the graph of tangent in your head. Remember, tangent looks like this. We have a vertical asymptote at negative pi over 2, and one over here at positive pi over 2, and it kind of looks like x cubed going up like that. So for what value, so the question is, what is the arctangent of infinity? For what value of tangent would we be at infinity? Well, again, this is the limiting case, right? So this thing's heading up towards infinity as what? We head towards pi over 2. So this will be pi over 2 minus, and the arctangent of 1 is pi over 4. So pi over 4. So that means that this integral converges. So the converges, so the sum n equals 1 to infinity, 1 over n squared plus 1 converges. Now, don't make this mistake. Just because the integral added up to pi over 4 does not mean that this summation necessarily adds up to be pi over 4. All we can say is that it actually does converge. All right, let's do one more of these. I'm actually just going to squeeze it right here. Let's do the sum n equals 1 to infinity of n over n squared plus 1. Now, we do want to do our term test real quick, and we did this a second ago, right? The limit as n goes to infinity of this was 0. Remember, that told us nothing. So let's try our integral test. So let's let our f of x be x over x squared plus 1. Remember, we're only looking at this from 1 to infinity in this case. Those are our bounds. So let's see. The bottom's always positive. The top will be positive if we use values from 1 to infinity. So this is always positive. To tell whether or not this is decreasing or not, we're going to need to do our derivative. So it's going to take just a little bit of work. So f prime of x, we're going to do our quotient rule. The derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared, which is going to be x squared plus 1 minus 2x squared all over x squared plus 1 squared. So it's negative x squared plus 1 all over x squared plus 1 squared. Okay, what can we say about that? Now remember, we're only looking on the region from 1 to infinity. Well, the top's always, the bottom's always positive. At 1, it's actually 0. But if you notice, anything bigger than 1, this is actually going to be negative, right? Because that's going to be negative squared plus 1. So any value bigger than 1, this is negative, so we can say that this is decreasing. And since x squared plus 1 is never 0, this is continuous. And yeah, you got to go through all those steps. So we should be able to do the integral from 1 to infinity, because we started 1 here, of x over x squared plus 1 dx. Now, limit b goes to infinity, 1 to b, x over x squared plus 1 dx. All right, this is just going to be a u du substitution. If I let the bottom be u, the derivative of that would be 2x. I don't have a 2. I'm going to pull out the 1/2. You could put the 1/2 right there if you want. So what is this going to end up being? This is going to be, get that out of here. Need to scribble that to make sure we can do it. So we got 1/2 limit as b goes to infinity. This is really, and you don't have to do it, this is really the integral of du over u, right? Because that was our u, that's our du. So this is going to be the natural log of the absolute value of x squared plus 1 evaluated from 1 to b. So this is 1/2 limit as b goes to infinity, natural log of b squared plus 1 minus the natural log of 2. Now I changed from absolute values to parentheses because that's always positive, so I don't need those. All right, so what happens to this as we go out to infinity? Well, the natural log of 2 is some number. Small number, like 0.6 something, I think. So what happens to the natural log as the values you plug in get bigger and bigger and bigger? Again, it's amazing how helpful knowing what the picture looks like, because I know the graph of the natural log looks like that. So as I head this way, this thing is, even though it's going up really, really slow, it's still going up towards infinity. So this is going to be, get that out of here for a little bit more room. This is going to be 1/2 of infinity minus the natural log of 2. Well, that's still infinity, right? Half of infinity is still infinity, which means the integral diverges. So the sum n equals, where are we starting? 1 to infinity, n over n squared plus 1 also diverges. Okay, so notice here in this case, this is one of those to where we did the nth term test and it did go to 0. But just because it went to 0 did not mean that it converged. In fact, it diverged. So when you're doing the nth term test, you're not looking for things going to 0, you're looking for things not going to 0. If they don't go to 0, then they diverge. If they do go to 0, then you got to do some more tests. Now, we can actually use, still talking about our integral test here, even though I'm going to erase that, we can bring in one of our old results to really help us with a new type of series. We solved this in the past. It was the integral from 1 to infinity of 1 over x to the p dx. So we did this integral, and the question was, when we did it, for what values of p does this converge and what values does it diverge? And what we figured out at the time, we said that this actually added up to 1 over p minus 1 if p was greater than 1, and it added up to infinity if p was less than or equal to 1. Which means, so the sum n equals 1 to infinity of 1 over n to the p converges if p is bigger than 1, diverges if p is less than or equal to 1. So just from this result, because we know our integral test, then we can say that this is true, which gives us a very huge class of problems that we can say whether or not it converges or diverges just by looking at it. So if the question is, again, it's the same, converge or diverge, with a question mark, and if I said what's the sum, n equals 1 to infinity, 1 over n to the third, that's an n, all you have to do, you have to be able to recognize the form. You're like, hey, this has this form. By the way, this was called like a p integral. This is called a p series. I didn't write it here. So p series. All you have to do to say whether or not this converges, diverges, you say this converges because it's a p series. P equals 3, which is greater than 1. That's it. That's all the amount of work that you have to do when you're looking at P-series. Now, one special case of the P-series is 1 over n. So in this case, our P is what? Exactly equal to 1. So this actually diverges, and we would say it diverges because it's a P-series. Here, P equals 1, which is less than or equal to 1. There you go. Again, because it diverges, you just state the condition why it diverges. That's it. That's all the work you have to do. However, just because you're going to see them in the future, because they have some physical properties that we have to deal with, a P-series where our P is 1, this is called a harmonic series. And we're going to see how that shows up a couple times in our future. All right, so we went through 3 tests today. The nth term test, a very quick, easy test to determine whether or not something diverges. We just take the limit as n goes to infinity of the original a sub n, and notice, of course, both of these go to 0. If it doesn't go to 0, it diverges. If it does go to 0, it doesn't tell you anything. The next test that we saw was our integral test. And we said as long as the integral converges over that region, then the summation should. But we did have 3 things we need to test for: whether or not the function was positive, decreasing, and continuous. And then from that, we brought in one of our results from the past about our integrals, which gave us our P-series test, which is probably the easiest test out of all the tests we're going to learn in this chapter.